Okay, so yeah, I'm gonna do a brief overview of the PRIAM project. I'm gonna be very brief, so I will give more time to the partners to explain the technical parts. So about PRIAM, which is the term for Planning Regional Scale Multimodal Operation for Innovative Air Mobility Services, this is under CESAR project, and this is a topic for multimodality and passenger experience. We started on September 2024, and we are finishing the technical part by August, and then our 6 months of dissemination until February. And these are the project partners. No one is coordinating the project. Then is TML, Deep Blue, HiCai, and the NAC on the in charge of the different technical parts. Blue Nest as an Airports de Catalunya as end users of the tool, and then Airport Regions Council in charge of communication and dissemination. So starting from background motivation of why PRIAM, why we need this project. So as you may know, the European Transport Policy goal aims to connect 90% of passengers within European 4 hours. To do so, we are aiming at multimodal strategy combining high-speed rail and air transport, which indeed works well for cutting intercity travel times and reduce transport emission, but it still faces challenges in more regional areas. So if we want to call that is inclusive progress toward this 4-hour strategy, we need a new approach that also focus on regional mobility. And here is where the role of innovative mobility appears. So you may know emerging aircraft technologies could improve this regional connectivity, but still the potential in regional mobility remains uncertain. So we still need more research in which are going to be the demand effects, coordination, reliability. So we need tools for this evidence-based implementation of services across Europe. So this is basically the goal of PRIAM, is to develop this data analytics and modeling toolset that supports a passenger-centric integration of EAM into regional transport networks across Europe. So in the project, we have 4 main objectives. First is to develop an impact assessment framework of how these EAM regional services are going to affect mobility within Europe. How are we going to address these regional connectivity challenges? Then we are going to develop and validate a PRIAM solution. We will present more about this tool in further presentations of this webinar. And then we are going to evaluate these case studies in this tool in 2 case studies, one in the Canary Island and one in the Catalan Pyrenees. And finally, from this result from the case study, we're going to derive a set of recommendations based on a cost-benefit analysis that will anticipate the impacts of deployment of these services across Europe. So in terms of methodology for the project, we are following these 4 activities. First, we have developed this problem definition. We have developed this EAM assessment framework. We have developed different scenarios. We have done there's research and literature review, plus some workshops and bilateral interviews with relevant external stakeholders. We are currently developing and validating the PRIAM solution in case all parts of this software development and case study specification on. This is currently going on. And after that, as I mentioned, we will derive this set of policy recommendations for defining the implementation of our roadmap for EAM. So that's was it from my side. So I leave the floor to Deep Blue to present the next part of the presentation. Thank you.
Thank you, Juan. Okay, now I should be able to control the slides. So in the blue, basically, we cover the main aspects related to the human-centered EAM requirements, scenarios, and impact assessment framework together with Nomon. It's a work that we carried on, Giusy and myself, from the beginning of the project. The most important part for these activities, okay, sorry, I have to request control again, were the involvement of different stakeholders in the definition of the concept of PRIAM and the main validation activities. As you can see here, the human-centered approach had different steps, starting from a literature review on the state-of-the-art of EAM and different concepts that I will present shortly. We then gathered all these gaps and needs from the desk research to experts that we interviewed. These experts were part of our external experts advisory board, and we came to intermediate outcomes. Once we had these outcomes, we had a workshop in Brussels with some stakeholders where we refined and fine-tuned some of these aspects, like the EAM needs, the scenarios, and the impact assessment framework. And this led us to have the final outcomes for the PRIAM project. So let me see. One slide back. Okay, so the desk research. Of course, as you know, PRIAM is an exploratory research project, so we had to start from the ground. There were 4 main topics we were exploring in the project. So the innovative air mobility vehicular concepts, business models, connectivity challenges, and passenger needs. For each of these topics, we explored the main concepts, the needs, the benefits, and the challenges. As you can see here, there are some of these highlights. More is included in the exploratory research report of the project. But as you can see, for example, for the main concept of the vehicular concepts, we found three eVTOLs configuration: the multirotor, vector thrust, and compound wings. We explored the needs related to these concepts, for example, the passenger transportation and the distance journeys they had to complete, some of the benefits of including such technologies in the mobility ecosystem, and the challenges that these concepts were facing at that period in time, so at the beginning of the project 1 year ago, like the regulatory hurdles, the ITM integration, and some technical improvements and societal acceptance that needed to be met. Once that we mapped all these needs, benefits, and challenges for these topics, as I said, we had a set of interviews. We gathered a pool of experts. As you can see here, we had different experts coming from aeronautical, drone operations, infrastructure development, innovation and deployment, and aerospace. And we had the possibility with them to confirm the gaps that we found, the benefits that we explored, and in addition to add some more challenges to these concepts. This then led us to the first PRIAM stakeholder workshop. It was held at the Airport Region Council facilities in Brussels, Belgium, where we collected a total of 9 stakeholders. Here, basically, we discussed mainly the needs that we collected for these 4 concepts, but also some of the scenarios that we were exploring in the project. In particular, I can provide you a brief overview of the regional connectivity challenges that we faced. There are also some references there that you can access. But basically, EAM faces 8 main regional connectivity challenges. The geographical barriers are of utmost importance, the limited public transport infrastructure that is today available, the sparse population density. Differently from urban air mobility, here we are targeting areas that are less dense in population and less connected with other transport modes, like high-speed rails. Cross-border connectivity issues, these also relate to the regulatory hurdles that we were mentioning before, the infrastructure that often is outdated or poorly maintained, concerns that goes to the environment and the sustainability. Of course, it goes without mentioning the aspects related to the visual and the pollution impact that these technologies can have. Some emergency medical services emerged as an important need to be addressed through eVTOLs, and some economic barriers to develop these infrastructures. Another interesting result that we found for innovative air mobility is the services that they would be more suited for in the short term and medium term period. They are not they are not prioritized, but the 5 main services that we found out to be relevant for this type of new transport mode are the business traveler transportation, the leisure passenger transportation, the emergency service transportation for medical goods and patients. This was ranked almost as the most important and the most feasible for the short-term period, and also travelers that need to go from to different airports. And this is where EAM has a real value, the communities in small and rural areas that are not well connected to the main grid and infrastructure. Just a brief overview of the case studies so that you can have a better understanding for the presentations that will follow. In PRIAM, we focus on 2 main case studies, the Catalan-Pyrenees and La Gomera, Tenerife in the Canary Islands. We have in the consortium we have the partners Aeroport de Catalunya and Blue Nest that respectively cover the first and the second case study. These are very interesting case studies due to their geographic limitation, for example, the Pyrenees in the first case studies, or the sea around the islands in the second case study. And as you can see here in the highlights, basically, for the Catalan Pyrenees, we have different small airports that are not well connected between each other, or, for example, the ski resorts in the Pyrenees in the state of Andorra. While in the second case study, between the 2 islands of the Canary Islands, we have different transport modes, mostly ferries and aircrafts, but this makes the journey between the 2 islands very long. And so here we can see that EAM could be very useful. As I was mentioning a little bit earlier, these 2 case studies led us to the definition of scenarios, in particular mountainous regions and intra and inter-island connectivity, as you can see in the right part of the screen in the table. And thanks to the interviews that we had with the experts, we decided to divide the scope of these scenarios into time horizons, 2035 and 2050. Basically, the reason behind this was because in 2035 we expect eVTOLs to be piloted, while in 2050 we can imagine them to be autonomous, and also for the aspects related to regulation, ATM, and use space integration. We also provided description for these scenarios, and they were included in the concept outline of the project. Lastly, this was an effort mainly made by Nomon, together with us, the Blue TML, and the other partners, which was the development of the impact assessment framework. As you will see in the later presentations, PRIAM is developing different solutions for the project, and we need, of course, to assess them. And we came at the end of the process, of the human-centered process, to 6 key performance areas to be explored. So, for instance, the passenger experience, the demand, the cost efficiency, the environment, the operational efficiency, and the capacity. And for each of these key performance area, we have different key performance indicator, KPIs, that will help us to measure the performance of our PRIAM solution. There are also some KPIs that can provide examples to you. But if you want to access the full list of these KPIs, they are included in our documentation. And basically, the validation of these impact assessment framework scenarios, case studies, and gaps and needs from the EAM perspective led us to the subsequent development of technologies in the project. So I close with this on the human-centered part and leave the floor to the next presentation. Thank you.
Okay, thank you, Francois. So let me take the control again. I think now I have it. Not sure. I'm not sure, Elena, if I can continue with the. Okay, no, yeah, that's it. Thank you. So thank you, Francois. Also, I'm going to continue the presentation with basically the PRIAM solution overview. This is basically just one slide explaining what the PRIAM solution is and how it looks like. Later on, I will give the floor to different partners so they will explain the different components of the solution. So as I mentioned previously, the PRIAM solution is a data analytics and modeling toolset that supports this passenger-centric integration of PIM into multimodal regional transport network across Europe. So what exactly does this means? So we have envisioned this solution such as a 5-component tool. The 3 first components are more focused on describing the passenger behavior, while the last 2 components are more focused on the EAM service characterization. So the first component is this EAM attention modeling. So the objective of this component is basically determine which passenger groups are more prompt to use these EAM services. So for doing that, we have conducted a survey, and we have tried to analyze the survey and see which passenger groups are more likely to use these kind of services in the future. The second component is potential demand monitoring tools. It's basically analyze the demand, so which is the potential demand for EAM. So for that, we have used different geolocated data sources to analyze how are the mobility patterns in the areas of the case study. So how people are moving, which is their behavior, how are they moving, which is their profile, this kind of aspects. Then the third component, this EAM-induced demand and modal shift modeling, is going to use the 2 previous components. Now we know how the passengers are moving, which are their patterns, which is their profile, and we know which passengers are more prompt to use these services. We are going to develop a set of models that are going to be able to explain which passenger demand these innovative and mobility services are going to capture. So it means mobility that was already using another kind of mode, bus, train, ferry, whatever, which are going to be captured by these EAM services, but also which demand are these services going to induce. So now the implementation of EAM services are going to make these regional areas more connected. So maybe they are going to induce some demand that was not previously there. So these are the models that we are going to develop, that we are currently developing right now. Then once we have this, the next component are more focused on the characterization of these EAM services is this EAM network planning. So basically, this tool is going to say, okay, now that I know which is the demand, which passenger groups are more prone to use this, I know more or less which is the demand that these services are going to capture. So this tool is going to say, okay, which is the optimal location for placing these vertiports. And well, this is not exactly direct because this requires iteration, because depending where you place the vertiport is going to affect to travel time and travel cost, and is going to affect which demand is going to be captured. So this is a little bit iterative. And finally, the last component, which is now that I know which is the demand that I'm going to capture, where the vertiports are located, this component is going to say, okay, so how this EAM service should operate in order to optimize the performance of the service. So how many vehicles do I need to allocate the maximum demand? How we should plan this service in order to cooperate with other more traditional mode of transport. This is what the last component is going to do. So this is basically everything from my side. So I leave the floor. I'm not sure if I can. Yeah. Okay. Yeah. So then I leave the floor to Aikai to present this part of the this component of the tool.
Yeah. When I'm just asking remote control, but I'm not sure I'm gonna get the control on the screen.
I can move it for you. No worries.
Thank you. Okay. So there are many dimensions to measure on the capacity to or interest to use this new air mobility technologies for rural areas, actually. So what we did in this task was just to create a model that would discuss and define how to study propensity and adoption levels of the future populations of a certain rural area. So the concern was how to model via state preference survey what might be the future profile of the populations if we can just make a method to detect it in order to satisfy, let's say, the purpose of fitting the right service to the right population area. That was basic within this modeling the state preference survey. So clearly the background information, demographics, the kind of mobility patterns were asked upon not a very large and huge sample, but a pretty much big sample of more than 200 subjects that were just telling us the background information and the interest, the adoption, or the wishes and the likes on using the system. So having in mind that we were just modeling some questions within the survey, the stated preference survey, that could hit and could identify some of the preferences by the future users, we started creating clusters. We were trying to model clusters. And Elena, can you just skip down one slide, please? So we've been applying a classic AI method, an unsupervised method. Just about the technical stuff is just machine learning, but that gave us a chance to first cluster and differentiate higher adoption propensity subjects from the lower adoption propensity subjects. We were at the beginning, just basically because it's a research, we were using all the information available from the survey and all the variables. I'm pretty happy that we in this task, we were just capable of identifying profiles that were hitting more on higher adoption and propensity levels. That is important because actually we were discovering that certain properties of a population is much more inclined and wishing to spend time, economical resources, and operations in their commuting using these new technologies, the PRIAM services. And other profiles actually were exactly or towards a limited kind of adoption or propensity of those. And at the beginning, we were just identifying out of many features, 18 features, variables that were very useful for the clusterization. And if you can see in the table, we basically were capable of splitting cluster 1, higher adoption propensity level, from cluster 0. That seems quite trivial, but actually, if you think about it from a forward-looking perspective, that gives a leverage to a municipality to keep an eye on the projected population into a zone, and then to satisfy that projected population and know in advance, maybe 10 years in advance, what might happen if we just build up the PRIAM services as we would like into this project. Clearly, some of the clusters in the first results were very much oriented towards nationality and the areas. Elena, can you just keep down one slide? When we decided to refine the analysis, the clustering were just hitting more or less the same arguments, but we were much more confident in reducing the undue leverage of socioeconomic factors into the equation and studying basically the adoption level for the future population into a specific zone in Europe. What might be the profile that might attract more the interest of using that service that PRIAM is just suggesting. And that is about the mode of regional trips, the concerns of privacy, the frequency of regional trips, the importance of the environmental arguments, and so on and so forth. Various arguments define the profiles of these clusters. And the clusters basically represent what a specific population might be more inclined or not. Elena, can you just skip down one slide? So to conclude this, because this is one angle of the modeling that we created in the PRIAM project, is that actually projecting the user profiles, high adoption levels at least, for certain municipalities will allow us certainly to have an idea, an estimation of whether the expected population would be fit to what we're going to provide them as a service. Clearly, this is a kind of a projections that can be done and can be benefited by the municipalities in order to orient the way they design the future offers. Because the problem is not, technically speaking, only defining the clusters. The type of profile much more oriented towards what we are offering in this project is to fit that expected population to specific areas. And the areas in Europe are very different. So, but with this clustering, we can just improve the deployments and optimize the service solutions and the effort to provide certain service provided in certain rural areas by studying the adoption that is most likely to occur for that projected population. And that will reduce risk. So minimizing the risk of deploying out-of-scope services, one of the big damage is to be very scientific oriented, but not realizing that population projected into a certain area in a specific time framework in the forward oriented solution has to be reflected by what we're going to create as a service. And creating a service like the PRIAM service, air taxes and the like, will take time and effort. So if we right fit the effort with the expectation of the population, that's what we did in the modeling the adoption level within this task. Yuan, I finished the conversation here.
Thank you, Daniele. So I will continue with the next component of the PRIAM solution. I think, okay. Yeah, so the objective of this component, as I mentioned, is to try to develop algorithms for understand who passengers are moving within a regional area. How are they? Which are the mobility patterns, the passenger behavior. So for that, we are using geolocated data, more specifically mobile network data. I will explain exactly which kind of data is this. And then additional data sources such as the census, transport network, surveys, etc. So we do a process of data analytics and fusion in order to have this characterization of the passenger behavior. I think I cannot pass the slide. I mean, I don't know exactly why, but yeah, thank you. So what is exactly mobile network data? Actually, what we have are the registers of the different devices when they are connected to an antenna. So what we have is the information about which antenna different users have been connected to. Also, we have the different location characteristics of the antenna, so we can define how the passengers are moving, and also information on passenger social demographics, age, gender, nationality, and so on. So exactly how can we use this data to understand regional mobility patterns and passenger behavior? So in the next slide, I have presented a video. You can press play, Elena, or click next. Okay, thank you. So this is an example of the kind of data that we have. So here's the sample of a person at Madrid. So at some point in the morning, they moved to their work location in the outskirts of Madrid. He spent there the day, and then at some point in the afternoon, they start moving again to their home location. And then the passenger is captured again in the airport, Madrid airport. Then the passenger appears again in Palma de Mallorca, and then we can see how they move to some activity in one area, and then the place where he will stay overnight. So this is the kind of information that we have for mobile network data. Okay, this is not GPS. It's but from that we can track the sequence of antenna and define how the passengers are moving. This is an example for an airport, but this is totally applicable in other areas, regional areas, and so on. So next slide. Yeah, that's one. Okay, so what we have done is to apply this process for analyzing this kind of data to the different places. So here we have the results from Tenerife, La Gomera. As Francois explained a little bit, these are two islands in the Canary Island. The only way to go there is by plane or by ferry. So with that, we can analyze the annual demand between Tenerife and La Gomera to analyze if in case we have to include these EAM services, if we have enough demand during the whole year. So for example, we can see here that although there is some demand during the summer, the demand is quite high during the whole year, which is interesting. Next slide. Thank you. Also, we can analyze from which parts the passengers are traveling to La Gomera. For example, this is the island of Tenerife. The image on the left displays from which areas the passengers are moving to La Gomera via ferry. So the ferry is in the south of the island. So we can see that all the passengers traveling by ferry start their trip in the area next to the port, and then the passengers traveling by plane start their trip in the areas that are more near the airport, which is in the north part of the island. This also gives us an idea in case that we want to place the vertiport where this vertiport should be placed already. In the next slide, I will present the same information, but for La Gomera. So in the case of the passengers traveling by ferry, we can see that most of the demand is coming from San Sebastián de La Gomera, is the yellow area in the east of the island, which is the main port of the island. And in the case of passengers traveling by plane, we can see also that passengers that prefer this mode of transport are located more close to the airport in the south of the island. So the main way of going between these areas is by ferry. In the next slide, I also present which routes. Ferry routes are the main ones. So, for example, we can see that most of the people is traveling from Los Cristianos, which is the port in the south of Tenerife, to San Sebastián de La Gomera, which is the main port in La Gomera. But also there are other routes to also the south of the La Gomera and also to the west part of La Gomera. Although this route is not that popular. This also give us information about if we want to start these EAM services, where we should, which kind of routes could be of interest for the operator. In the next slide, also I present information that can be derived from mobile network data, is socio-demographics. So, for example, we can see here we are comparing the behavior in January versus August. So we can see, for example, that in August we have more national passengers traveling between Tenerife and La Gomera. Also information about which are the nationality of these passengers as well. At the time of starting these new services, we can see that maybe there are some profile of passengers, some nationality that is more prompt to use these services, maybe coming from the information that we have seen in the previous component, the information presented from Daniele. So with this kind of information, we can also infer which is the nationality of the passengers, with the place of residence, and start to extracting some interesting insights. The same kind of information can be extracted regarding the age of the passengers, etc. Another sociodemographic information. The next slide, I think, is already the application of the case study to the Catalan Pyrenees. So we have done more or less the same, analyze from which areas the passengers are going to the Catalan Pyrenees. Here we are presenting, in this case, again, the demand through the whole 2024. So we can see that, again, the most typical year is the most busiest month is August, but it has good demand, high demand during the whole year. But there's also in this broad area, so the passenger behavior can be different in different areas. So, for example, in the next slide, we can see, here, for example, this is the example for Baqueira, which is one of the main ski resorts is located. So we can see a lot of demand during August, but also big demand during the ski time, which is January, February, March, also December, and very low in the rest of the months. So this is also interesting at the time of starting this EAM service, these EAM routes. So how is it going to be the demand during the whole year in case these kind of routes are going to be used for passengers during the whole year, or are going to be just stationary. So also interesting insights that we can derive from mobile network data. In this next slide, I present also information from which areas the passengers are accessing to the Catalan Pyrenees. So we can see, for example, the left is we present the Catalonia area. So we can see that most of the demand is coming for Barcelona and areas next to Barcelona, and also from the areas next to Lérida, also main city within Catalonia. So we start to think that these EAM services could connect these two locations with the Pyrenees. And this is the kind of information that we can derive from mobile network data. Also, we have do a similar analysis with the rest of Spain, which the demand is lower, but we can also see a lot of demand coming from the provinces that are next to Catalonia. So a lot of people coming from Madrid and also from Valencia. But for this case study, once we have analyzed the demand, we have focused just on the Catalonia area. And next slide. So this is exactly what we have done, and we are really already analyzing. So the next steps are calculating the travel time and travel cost. So what we are doing now is, once we have analyzed demand in the different case studies, we are using OpenStreetMaps to calculate travel times by road. This is the transport network study from OpenStreetMaps that we are using, and also use GTFS data to calculate travel times on different transport modes, such as train, bus, plane, etc. And then once we have these travel times, we are going to calculate the travel cost, assuming a cost per kilometer in case of road, and also doing some web scraping, looking for some prices in ferry, plane, in the different areas. This is something that is currently going on. And with that, I conclude my part of the presentation and give the floor to Timel.
Yes, thank you very much. Yeah, I have control over the slides. In this component of PRIAM, we are working on travel demand and calculating and estimating modal shift and induced demand for IAMs, innovative air mobility. And we would like to also study how travelers trade between travel time and travel cost, and compare the IAM demand with motorized and non-motorized modes, technically with other modes which are available in our case studies. I don't have control over the wait. I think now I have control. So in order to do so, as my colleagues already mentioned, we have done an stated preference survey, and in this survey we have asked from the participant different questions, among which we have asked for our case studies what modes of transport they are choosing. They would choose if they want to travel between the origin and destinations that we have provided in our case studies, for the current modes of the transport, and for the future modes of the transport, which includes IAM as well. So with that, we can see how travelers are shifting from the current transport modes to the future transport modes, including IAM. For example, in this case, which is between Tenerife and La Gomera. So on the left, on this Sankey diagram, you can see the current modes of transport, which are ferry, plane, and the option for not traveling. And the right side, you can see the future modes, which are IAM, ferry, plane, and not traveling. And so with that, we can see how the travelers are shifting from the current modes, and we can see from which modes of transport the IAM mode is shifting. Yeah, that's the same diagram for the other origin and destination points that we have in our case study, and we can see here most of the demand for IAM comes from the taxi and car travelers. This is the next one in the other case study that we have in the Catalan-Pinaris region, and the origin and destination for these is between the Andorra de la Vie and the airports, the Urgell, and here also we can see how the travelers have switches from bus and taxi and car travelers to IAM, and most of the travelers are switching from taxi to IAM here. This is also the next one. I'm not going to the detail of all of it, but yeah, this is just to show you that with the survey that we have done, we can see how the travelers are switching between different modes. The next analysis that we have done is that based on the survey that we have conducted, we have the choice sets for all of the respondents. So based on that, we can develop a discrete choice model. And with this discrete choice model, we can estimate the demand and have some coefficients and have some estimates on how different features of traveling impact the choice of each travel mode. For example, here in this model that we have developed, we have aggregate the modes into motorized modes and non-motorized modes and the IAM. So with that, we can see the impact, how the travel time and travel cost is impacting the choice of the different modes of transport. And as we can see here, all of the signs make sense. The more travel time we have and the more travel cost we have, the less the utility of each transport mode would be. But the interesting point is that the coefficients for travel time for IAM is much more than the travel time for motorized and non-motorized modes, which reflect the fact that IAM travelers are much more sensitive to travel time. So this is why makes the travel time of IAM services really important and a significant factor. Also, with this discrete choice modeling that we have done, we can also study the value of time for the travelers, which is the trade-off between time and cost, and express how much users are willing to pay to save 1 hour of traveling. So the value of time for IAM is around 120 euro per hour, but this value is much less for motorized, including car, taxi, bus, and non-motorized, including train. So which also makes sense, and which means that the IAM travelers are much more willing to pay for saving time. Another study that we have done using this discrete choice model that we have developed is an break-even analysis. This break-even analysis, this break-even actually shows how much price premium can IAM charge if it saves a specific amount of minutes. I'm not going into the technical detail of this break-even analysis, but for example, this analysis shows that for a baseline, for a 1 hour travel of motorized modes, if IAM saves 45 minutes, then the model supports the fact that IAM can cost 30 euro more than the other modes. And these kind of, this is just an example of the results of such analysis, but these kind of analysis can help the policymakers and decision makers when they want to implement, for example, the cost and how they want to regulate the cost and these kind of aspects regarding IAM. Using this model and based on the results that I shared with you, so we come up with the fact that, as I mentioned earlier, the most important factor in choosing IAM is the IAM travel time, and this is very strong in the model that we have developed. There is a very strong sensitivity to delay and access time. So it's and 1 hour IAM time is equal to 117 perceived cost, and we have put it on a relative scale and in order to understand the importance of each factor on choosing IAM. And as I mentioned, the most important one is the travel time, and the second one is travel cost, and the other one is the other factors like the unobserved factors that we have not have in our current model. And then. So what does this mean for IAM design and policy that we are currently work on? In order to have better the time saving for IAM, then we should think more about the vertiport locations and access and egress times and boarding time and that kind of stuff. But in short, one sentence, we can say that IAM only succeed when it's clearly faster, and the pricing must follow the performance of IAM. Another study that we are currently working on, and it is under development, is in order to understand the induced demand of IAMs. And in order to do that, we are developing a generalized cost for the current trips that people are making in the 2 case studies that we have based on the mobile network data that earlier Juan mentioned. So we are developing a generalized travel cost, and we relate the generalized travel cost with the trip frequency. And with that, we can come up with the induced demand for IAM as well. With that, I would give the floor to Lucia. Thank you very much.
Hello. I don't know if I can take control of the presentation. Okay, you will do it. Okay. So yes, I will talk about the vertiport location part of the PRIAM project. So as my colleagues have explained in a previous talk, the main challenge here is for IAM mobility is ground infrastructure. Today, even if IAM vehicles are certified to fly, the infrastructure for them to do fleet operation is not present. The current infrastructure, which is heliports, also lacks the charging facilities that are necessary for these operations. And also, in the PRIAM project, we are in the context of regional connectivity, which follows the flypath vision that Juan has explained already. So 90% of the door-to-door trips have to be made in less than 4 hours, and this is very good if you go from capital to capital. But there are many rural areas in Europe that are not as well connected by ground infrastructure, and building and maintaining this ground infrastructure is expensive. And often this is one of the reasons why public transport alternative for this region is often lacking. So what we want to do in PRIAM is to help IAM being a potential solution to bridge this connectivity gap. And to do so, vertiport location and planning is critical for its success. So we can go to the next slide. Yes, so what are we going to use for the vertiport location tool? Well, as input, we have first mobile network data. And as we have seen in the previous presentation, it has many advantages. One of them is that we have a very large sample of the population. We don't have reporting biases. And this type of data captures not only socio-demographic information, but also seasonal variations, as we have seen. And we are able to track not only residents to the areas, but also people that might be visiting from other regions and even from other countries, which is a data which is usually typically not available in this kind of surveys. And also, we have very high resolution, which is at district level or even below, depending on the case studies. We also build upon the survey. As Besat has explained in the previous talk, they are developing discrete choice model that we will apply to the mobile network data, and this will give us more information about IAM captured and induced demand. And knowing this, knowing how people move now and knowing how people will move in the future, we will be able to tell which are the best locations to place this ground infrastructure, which are the vertiports. And this we will do, of course, in the 2 case studies of the project, which are the Catalan Pyrenees and the Canary Island. In this context, they are particularly interesting because they provide different challenges with respect to regional mobility. One is mountains and the other is islands, so there is water. It's from the operation point of view, they are quite different. And also we have the 2 time frames, which are 2035 and 2050. So the idea is to be able to see what are the optimal locations in all of these multiple contexts. And this tool is based on 2 previous SR initiatives, which is mainly the Maya project and Vertiport Location Engage KTN project as well. So we can go to the next slide. So in the tool that we are developing, we have as input our mobile network data and the discrete choice model, as I have just said, and this will give us the potential IAM demand. And now we are in the process of integrating these 2 data sources to the tool we already have. We have our zoning, which is tailored to the 2 case studies, and now we can play with the different type of IAM vehicle that we want to model, for example, the EHang or the pipistrel vehicle. And we can also play with the distance, with the minimum distance of IAM trip below this threshold. We consider that no trips are made by IAM, and we can also add like restricted areas, for example, airport runaways and stuff like that, to be as realistic as possible. And the inputs we have specifically for vertiports are the number of vertiports, which is we will define it in the context of our case studies, how many vertiports we want for each case study and each time frame, what are the operating costs of these vertiports, salaries, maintenance, connection, infrastructure, so on and so forth. This we will adapt and tailor to the case studies, and we will also add, if necessary, pre-selected locations. So, for example, heliports that have been converted to vertiports in the context of these case studies. And also, for example, like the incomes or the search bar, everything will change. And what we want to be is as exhaustive as possible, so that we have our simulation is as close to reality as feasible in this context. So now we can go to the next slide. Thank you. And the objective function of this vertiport location optimization tool is still working in progress. So now we have, at the moment of today, we have several possibilities that we are still tweaking a little bit. The first one is we can suppose that there is no public investment, so all the costs of building and maintaining the infrastructure are carried on either by the vertiport operators and the drone operators. We can also think of a scenario in which there is some public investments to build these infrastructures to connect these regional areas. And for that, some costs may be covered by the state, so they will be reduced to zero in our objective function. And also to compare the, let's say, realistic best location of vertiport to the theoretical best location of vertiport, if we only take account the demand between the area, we can also do that and put all costs to zero and just try to maximize the demand and see this. So how this allows us to see how the costs are affecting the locations of the vertiport and the final demand that we are able to capture. And the final objective function is still work in progress at the moment. So we're still working on this. We can go to the next slide. Yes, and these are some preliminary results that we have done in a reduced study of the Pyrenees areas. So the two images looks practically the same. They're the same assumptions, but slightly different objective function. The one on the left is taking into account all the costs that we have at the moment, and we have made some guesses for all the costs, some educated guesses. And we have placed 6 vertiports, and we can see that 4 of them are in the Pyrenees. These are the red dots, and then 2 of them are more to the south, close to the Igualada region. I forgot to say this mini case study is Catalonia. And if we change the objective function and we remove the cost of the floor, we can see that we have 3 vertiports in the Pyrenees, and we have 3 of them close to the Igualada region in this preliminary study that we did. So right now, what we are doing, one of the things we're doing is seeing how sensitive the optimization is to this type of parameters in the context of the case studies. And that's it from my side, I believe. So yes, I give the floor now to Enak.
Hello, everyone. Okay, I have requested remote control. Okay. Hello, everyone. In this part, we are going to provide IAM service optimization models. And so firstly, we do a literature review. We try to find out the decision variables and the commonly used algorithms and some KPIs for those operational optimization. And then we conduct a research gap identification. And we found out that we are going to solve 2 NP-hard problems in IAM service optimization. And we need to jointly optimize those 2 NP-hard problems. And then we develop a heuristic-based optimization model, and we publish a CISA Innovation Days conference paper. And as for the case study analysis, we're focusing on the Catalonia, Pyrenees, and the Tenerife, and the second case study is ongoing. And in the future, we're trying to compare our proposed heuristic-based optimization model with exact algorithms, and maybe we can publish a journal paper. Okay, and let me clarify those steps one by one. Okay. Sorry, there's some mistakes. Okay, so for the desk research, we found out that IAM integrate in multiple model networks can be reduced to 2 NP-hard problems. The first one is to optimize the movement of IAMs, and the second one, we should also optimizing the passengers' journeys. Since we are focusing on multimodal networks, and the passengers plays an important role in connecting different modes. So we should both optimizing the IAMs and the passengers, and there are 2 joint optimization problems. Okay. And so, as we all know, it's an NP-hard problem, and we cannot find exact resolutions. So we proposed a heuristic-based model to solve this problem. And we can see in this flowchart, firstly, we estimate the demand and the supply, and then we construct a time-expanded transport network graph. And thirdly, we run a star to optimize passengers' journey, and we run dynamic programming to optimize the trajectory of the IAM. Let's see the results. We can see in left is connectivity, accessibility without IAM services, and we can see the most of the vertiports in the mountain area is isolated. And when we provide 550 IAMs, we can see that most of the vertiports connected with each others, and so the improved accessibility in remote areas and a minimal charge in urban regions. And it could be due to that in the urban areas, passengers have much more cheaper transport options and making IAM least likely to be chosen. Because in this setting, traveling with IAM is more expensive than ground transport modes. But we can modify this setting in the future. And as for our next steps, we develop an exact model, and we formulate the optimization model as a mixed integer linear programming based model, and this is our objective functions. And we try to minimize the passengers who haven't reached their destination at the end of the time frame, and we try to minimize traveling cost. And the following 5 constraints are considered while solving these problems. We consider the existence constraints, the dispatching constraints, the reachability constraints, and the flow constraints, and the capacity constraints. Okay, and then we validate our proposed models, and we can find out that okay, let's see. The omega means the efficiency that balance the fulfillment rate and the traveling cost. And when we increase the parameters, we can find out that the fulfillment rate will firstly increase and then decrease, and the optimization time will decrease when the value of omega at 10 powered minus 11. So we set the omega as 10 powered minus 11. And then we also find out that our model complexity will linearly increase with increase of the number of passengers. So it's a very good properties. It means the complexity will not increase rapidly with number of passengers. Thirdly, we also find out that the time frame size will influence the performance of our model. And if we increase the time frame size, we need to take a lot of time to solve this model, but it will also means a very good fulfillment rate. Okay, and this is our next steps, and very thank you for your attention. Thank you.